Now, so let's look at where contemporary science is. In 1992, one very brave physicist called Edward Fredkin, I think at the time he was at MIT. He's a pretty high-powered physicist. He then went to Boston University. I think he's now at Carnegie Mellon. He was an important enough physicist at MIT that they have a Fredkin Prize there now in his name. So another big gun in the field. He stood up in a society, a physical society, a place where you give papers, and he gave one that came to this conclusion. It said, the entire history of our universe is computable. And he reached it through information theory. He was a physicist, but he also did a lot of work with information. So he said, reality is digital. He says, everything else is digital. We know everything else is digital except space and time. And he says, that's just because we can't measure fine enough. So that's digital too. And that solved his physics problems, but it led him to this place where he said, reality is either a computer itself, it's implemented on a computer, it's a simulation, it must be digital, it's essentially information. So this is Edward Fredkin in 1992 standing up in front of a bunch of physicists. And he, like I said, he was a brave man, but because he had so much stature, he survived well and his career went on. He was stuck though, because the first question is, Dr. Fredkin, if we're computed, who's computing us? Where are we computed? And he said, well, I don't know. He says, the physics, the math leads me to this result. He says, I can't answer that question. It doesn't give me the answer, but it tells me that this must be so. So that was his presentation. Now today, digital physics is kind of an acceptable branch. It's out on the fringe, but there are literally hundreds of digital physicists, and they're spread all over. There's a pretty extensive group of them in Italy, and there are lots of them in the US. And so digital physics is now a part of physics. Fringe, but a part of physics. Well, he said the computation must be in other. And that's because he didn't know what else to say. And he put other in quotes, just like I did. And that's all. He says, we don't know where other is. Well, what Fredkin didn't understand is that consciousness is the computer. Okay. Now, Nick Bostrom, he's at Oxford now. He's the head of a department at Oxford. Again, not a lightweight renegade physicist from Huntsville, Alabama. These are high-powered guys. He wrote a paper. He's also a philosopher, physicist and a philosopher, and he's taught both at universities. He has degrees in both. He wrote a paper some years back called, Are You Living in a Computer Simulation? And in his paper, he said, one of these must be true. It was a real fun paper, real interesting paper. He says, one of these must be true. It's impossible. And he studied that for a while, and he came to the conclusion that it was impossible to say that it was impossible. So then he said, well, if it's not impossible, then it's unlikely. And he studied that for a while and said it's unlikely to say that it's unlikely. Well, having gotten that far, he said, well, then, it's almost certain that all of us, are living in a simulation, that reality is a digital simulation. Now, we have Brian Whitworth. Brian is not as well known as Fredkin or Bostrom. Brian has just published actually another paper on this subject. He's published 2, and he's got 3 more in the hopper. And what Brian Whitworth did, he's a mathematician, specializes in digital science from New Zealand. And he said, well, listen, guys, you have digital physics, and it's been around now for 20 years or so. And let's just see, does this idea of us having a simulated digital reality, a virtual reality for our physical reality, how does that answer the mail in physics? So he started with the 2 like in separate columns. Okay, if you start with the traditional physics, reality just came from nowhere, the mystical assumption, and you go with that. That is what he called the objective reality theory. And then you go with the virtual reality theory, and you see how they answer the questions. And his result at the end of his paper was, wake up, physicists. Look, assuming that reality is virtual answers the questions better. suits the data. It fits the data better than assuming that reality is objective. And it's about a 20 or 30 page paper. And that was the case. I mean, he looked at all the details of physics, the things that mostly physicists would appreciate, and ticked them off together, you know, which one could answer what and what were the explanations. A digital virtual reality does a better job at physics than an objective reality does. There are fewer inconsistencies. There are fewer things we just don't understand. And it covers all the things we do understand. Then he wrote another paper, it's not actually been published yet. I got an advance copy of it and sent him some comments and whatever. We communicate some. And this paper basically does the mechanics of space and time. Says, where does space and time come from in this virtual reality? And again, he does that. He compares it to the objective view, and he gets better answers. In other words, he fits the data. We know that certain things happen. That's what I'm calling the data points. We know the world works this way. Experiments tell us this. Now, physics has to tell you why. And assuming that reality is virtual and digital can tell why, fits the data better than so he derives space and he derives time, and it does fit the data better. So, why doesn't science kind of jump on this? Well, it's for the same reason that they didn't jump on Einstein's conclusions. All right, now what? Okay, it's a digital reality, and they have Fredkin's problem. What's other? How does it work? Where does it come from? And when you hit that wall, then it's like, well, let's not go there. Let's go back and do things that make more sense to us. So that's why it's not a bandwagon that everybody jumps on. Okay, so kind of the conclusions that we come to is that consciousness is the fundamental reality. Einstein and Bohm said as much of that, so did Wigner. Larger consciousness reality is a digital information system. Okay, at the most fundamental level, consciousness is information. At the most fundamental level, information is bits. And at the most fundamental level, bits are binary. Okay, so now how is that consciousness is just information? Okay, think of us now in this room. You're getting information. I'm talking, you're getting information. You're also getting information from the screen and the smells and the sense of this room around you. Well, what is that information? What is it? It's just data. Light particles, right, are going into your eyes. They're stimulating your retina, which produces a little electrical signals. It runs down your nervous system till it gets to the brain, and it produces neurons. Neurons move through synapses. Well, electrical pulses, they're discrete. Neurons are discrete. And what are those electrical pulses in neurons? They're just data. They're just encoded data. Your brain then interprets that data into this experience. Okay, so that's what's going on. Whether it's hearing is the same thing, stimulates nerves, nerves to neurons. So you got all this digital information coded in electrical pulses, neurons, and that's your reality. So let's take you out of this room, put you in a dark hole someplace, put you in an isolation chamber where you have no sensory input. And let's say that I can stimulate your optic nerve and your auditory nerves just exactly the way they're being stimulated now. What would you perceive in your dark hole of an isolation chamber? You'd perceive exactly what you're perceiving now. So then the question is, how can you tell the difference? How do you know you're not in a deep dark hole having your nervous system stimulated the way it's stimulated now, or whether you're here getting these light waves and acoustic vibrations? There's no way to tell. There is no difference. There's no experiments you can do that tells you what the source of your data is. It's just data. Okay? So now imagine yourself as consciousness. You're consciousness, and you have this data stream coming to you, and this data stream is interpreted by you as this reality. Okay? So you see how this kind of comes together. Your consciousness is data. You yourself are a subset of consciousness. So you are also data and information. Everything about you is data and information. Your body is all information. The cells, it's all information. Okay, so reality is just information, and it's also digital because it's not continuous. It comes in discrete chunks. Okay, so now we have consciousness as a system of digital information. Almost sounds like the computer guys have gone nuts, right? You know, they're trying to take over the world, you know, and own reality. But this fits the data. This fits the data points. This fits the science, and it fits. From this idea, we can derive both quantum mechanics, relativity, and metaphysics. It all falls out. Okay, so information is non-physical. Well, that's also a big hurdle to get over. I mean, this is the information age. You know, how could this be non-physical? Well, what you think of as information is not really the information. You're thinking of the media and the code symbols. Well, look at a book. You say a book, you know, contains information. It does. The media is the book, the paper. The code symbols are the ink. But where's the information? There is no information until a consciousness looks at those code signals on that paper and interprets them. That's where the information is. Information is meaning, content, significance. Information is not paper. Information is not ink. It's not ink even in words and letters. That's not information. Okay, that's media and code symbols. You don't get meaning and content until a consciousness interprets it. So the media and the code symbols, they allow for storage, like in a book, or transmittal, like over, you know, microwaves. So we can store it and transmit it in those forms, but that's not really information. It's not until we look at it that we get the content. All right, now, to get the, you know, to grasp the information, to get the meaning, you have to have a consciousness. Information is non-physical. How do you put information, you know, anything physical can be put in a volume, right? Can be put in a jar. How do you put information in a jar? You put a book in a jar, but a book in a jar is not information. Information itself is content, it's meaning. Can't put it in a jar, it's non-physical. Understanding requires subjective interpretation of the data relative to personal experience. That's what we saw on that slide with the two things that look like brains. We're coming to the same conclusion. Okay. Now, information systems and evolution. This is the next big step. Information in a digital system is represented by organized bits. If all your bits in a data system are random, there is no information. That's kind of the definition of random, is that there is no information if they're random bits. So the way you get information is you take bits and you organize them in a particular way, in particular patterns, and those patterns have meaning, and those patterns are symbols, and you end up with information. So information systems have entropy. Entropy is a physics term that talks about the level of organization. So a system that has high entropy has a lot of randomness, has little organization. A system with very low entropy has a lot of organization. There's another way of looking at entropy, and that is ability to do something, ability to have an effect, ability to do work, as a physicist would say. So if you have high entropy and a lot of randomness, you don't have much ability to do anything. There's very little effect that you can have. A low entropy system is a system that can accomplish something. It has content. It can do things, and we can take an example. If we took that laptop computer that's sitting on the desk there and we disassembled it into all of its components, every little washer and nut and you know, transistor and everything that's in there, we pulled out and laid in a pile on the floor, we would have increased the entropy of that laptop computer tremendously. Now we would just have a pile of parts. The pile of parts can't do anything. It's not even a good paperweight. We've reduced the functionality and its power to do something. Okay, and we put all the parts together, and the reason that they can make that computer is because those parts have to be assembled in just the right configuration next to each other. You can't just throw them together in a pot and shake it and get a computer. They all have to be just so. And all of that organization create something that's very powerful, that can do a lot. So that's the function of entropy. Okay, so lower entropy, you have greater power, ability to do work, and you have much more organization. Okay, so that's an important concept. Now, systems evolve to be more successful within their environments. Okay, that's evolution. And any system can evolve. We think of evolution as, cells going into aquatic life, going into land animals, ending up in people. We think of biological evolution, but everything evolves. All systems evolve. The economic system evolves. Political systems evolve. They de-evolve too. But they can change. They change themselves. Okay? And one way of looking at evolution is to say that as systems evolve, they are lowering their entropy. They're gaining more power, more value, more potential for what they can do, and they are more structured. They have less randomness in their systems. Okay, information systems also contain entropy. And any of you that might happen to be in information sciences, you realize that entropy is a normal term that information people use. They often use it in terms of signal to noise. Okay, entropy of information means the content. In information systems, you have a high entropy, you have a lot of randomness, you don't have much content. So it's a very natural process to apply entropy to information systems, particularly digital information systems. So here we have consciousness as a digital information system, and we have entropy that measures the effectiveness of that consciousness. Okay, consciousness is a self-aware, self-modifying system that's evolving toward lower states of entropy. Now, evolution requires a goal. Okay? Evolution requires a goal. Our biological evolution, the goals are two, right? Procreation and survival. Those are our criteria for successful evolution. In a consciousness system, in an information system, the criteria for evolution is reducing entropy. That's the goal. It's an information system. Okay, so let's talk about attributes of consciousness. Consciousness I have here 4 attributes. You have input. Okay, input's what we're getting now, right? That's the data stream I say that we're connected to. Now that defines experience. You have processing, which means you have to take that experience and do something with it. Was that a good experience? Was it not? You have to do something with the experience. You have to compare and assess. Well, how do you compare? What do you compare and assess it against? Well, you compare it and assess it against the purpose. And the purpose is to decrease your entropy. So you have an experience. Does this experience help you increase or decrease your entropy? And then you modify the input in order to move your system toward more profitability, the lower entropy. It's a simple kind of thing. You put your hand on a hot spot, and that's the input data. It hurts. So the processing says, it's burning flesh. This is not good. The purpose says, this is not helping me, get to where I need to be. The result is you pull your hand away. That's the way we operate. But everything operates that way. That's the way businesses and economies and everything that evolves basically evolves in the same sort of process. So then that's a loop. Keep going around in that loop. You modify, you have experience, you process. Is it getting you where you want to go? You modify, you have experience, and that's what we're doing here. So if we look at consciousness as a sentient, that means it interacts, it can react to stimulus. A sentient, self-aware, which means, those two means it's able to learn, okay? Data system. So that's what we call being alive. If you're sentient, interactive. Okay. So the other thing that you might notice about this, what else do you know that sounds like input, processing, purpose self-modification. Well, it sounds like a desktop computer, doesn't it? That's what they do. They get input, from the keyboard or from the internet or someplace else. They process. They have a purpose. We tell it what to do. We give it instructions. The purpose is to load this CD or whatever, and it gets, it manipulates what it has to manipulate to do what it does, and it's then self-modifying only in a very rudimentary way. We haven't gotten to conscious computers yet because it fails at the self-modification. Now, our computers do a little of that. We tell it to do some operations, and they will do some things where they modify and change themselves to configure it to our wishes, but it's very, very rudimentary. One day we will see conscious computers. Okay, so where did all this start? All right. Now, when you talk about where things start, there's always this problem because no matter where you start, somebody can always say, well, what was before that? So we have to also talk at the same time about limits of knowledge. Okay, so where we're going to start, though, is very much like the biologists start explaining evolution of physical life here. What they'll say is that you started with just the right chemical constituents. There was some amino acids in a nice, in a benign environment, and then maybe you got a little spark of electricity or whatever, and then presto, you got a cell. At least you got an organic compound, on the way to a cell. And then, of course, the rest of it is history, right? The cell divides, it learns to do better in its environment, and it grows and it splits, and it decides to be able to do separation of duties, right? It specializes into various things, and eventually you end up with us. But this then works the same way. You start with an assumption, and this is one of the two assumptions that this theory is based on. There's two assumptions that it's based on, and one of them is that consciousness exists. That's not too big a stretch. We all should agree with that. Everybody here looks conscious, so I think we can agree with that one. Consciousness at that time, though, I see it as like a primordial potential energy, if you will, that had the interesting capacity that it could be in one of two states. It could be this way or that way. So it's just a potential energy form that found out one day, just like this cell, kind of happened to come together, that it could be this way or that way. Okay, now if it could be this way or that way, eventually it probably got control of this way or that way, and kind of, played with that, and then it could be this way, that way, and the other way. So this way and that way is like a 1 and a 0, isn't it? And if you can change these states and duplicate them, then you can produce more 1s and more 0s. Eventually, that's so much fun that you produce patterns of 1s and 0s. And that becomes interesting. Again, evolution works toward lowering entropy. You're producing order here, right? What we're doing is lowering entropy by doing these things. So that's the natural way that evolution moves it. So then you do more 1s and 0s, then you get into patterns, and then you have patterns of patterns. And then a big discovery is time. You change 1 0, 1 0, 1 0, you keep changing it like that, and you have a metronome. Now you have a clock. So besides patterns of patterns, now you have sequences of patterns. So you can see that all of this is organization. It's all lowering entropy. The other assumption that I have is that of evolution. Evolution exists. Evolution is a natural force that works within complex systems that are able to change themselves. Any complex system, again, an economic system perhaps, or our biology system, or any other system that is changeable, then it evolves naturally. It changes state to be more profitable to itself. Okay? And that's just, so you take those two things, evolution, which is a fundamental imperative to modify in order to improve yourself or lower your entropy, and a potential that's capable of changing itself, that just was able to differentiate states. Okay, so that's the idea. So we say, where did that potential come from? You know, that's the Corker question, right? Well, where did that potential come from? And that's one where we just have to say, don't know. But I have a good reason for not knowing. And that is, it's outside. You know, that is consciousness. That potential then is this big consciousness system. It's outside of the ability of consciousness to see itself objectively. Unless you can see it from an objective viewpoint, you're not going to understand its origins. You have to be aware in the system that parents in order to understand the origins of what gets parented. That's just a fundamental logical thing. Okay, but what we can do is we can move that level of understanding out one level. And that's basically what we do with our knowledge anyway. You know, it's not that we have to know everything, but we can know something. And what we do is we tend to move it out. So we started, 1,000 years ago or so, and there was a flat Earth. Okay, and the flat Earth worked well. That's not a bad approximation if you don't travel too far too fast. The Earth kind of looks like it's flat. But then we got a bigger view. And as we got a bigger view, we got a round Earth. But the Earth was the center of the universe. The center, well, we didn't know about a universe. It was the center of the solar system, right? And then we got a bigger view, and we weren't the center of the solar system. The sun was, and we were just a player. But the next view was that we were our solar system was the center of the universe. And then, well, we got a bigger view, and we found out, well, we're just in a galaxy. Well, certainly we're the center of the galaxy, and then we're just a little spot on an arm of a galaxy, but this was obviously the only galaxy. And then we got a bigger view, and there's hundreds of thousands of millions of galaxies and so on. So the view kept getting bigger. And that's like an onion. You keep peeling back the layer after layer. You get a bigger and bigger picture as you get further outside and are able to objectively look at what you've got. So what we're doing here is we're not giving the final answer because that's not ours to give, but we're peeling the onion back one more layer. We're taking a bigger view, which enables us then to see everything that was there before, except we see it from now a bigger perspective that makes more sense. Okay, so that's really what's going on. All right, limits of knowledge. This is why we can't get to the end, and this is why you can't really get to the territory that you have to stay on the map. That we're always talking about models. We're always talking in terms of metaphors and symbols, and it's hard to really get to the real reality because all we have is data. All right, look at this this picture, and you'll see that it's systems within systems. The chain's not infinite. To think that it's an infinite series is not productive. But you can say that we can only see so far. There's no reason to say that it's an infinite series. Nothing real is infinite. Real things aren't infinite. Infinite is a mathematical concept that has nothing to do with reality. Okay, this tiny little red spot, that's us. Okay, that's our universe. The little red spot there is our complete physical universe. This little khaki spot outside of that red spot is what I call our system. That's our physical universe, and then all of that non-physical that interacts with our physical universe. So when Uncle Fred dies, Uncle Fred goes out here into this little khaki spot. Okay, so that's the non-physical part that interacts with our universe. So that's just that much. Now let's look at the lake out here. That would be the larger consciousness system. Okay, so what's out past the larger consciousness system, out here beyond the consciousness system? See, that's outside. Until you can get out there, then you can't look back at the consciousness system. Until you can get out here, you can't look back at our system. And until you can get out here, you can't look back at the physical system. You have to keep getting out to the next layer in order you can look back at the one before it. Well, here's my example. Let's say that our universe is modeled by a bacterium in the small intestine. I once in a lecture said the stomach, and somebody pointed out to me there are no bacteria in the stomach, and then somebody else pointed out that there are too, and they got in an argument, so I don't talk about that anymore. We go to the small intestine because everybody knows there's bacteria there, so we won't start any arguments. So that's a bacterium, and it's a bacterium in your small intestine. Okay, now think of the reality of that bacterium, right? It's just in there, it's dark, it's black, it's full of acid, it likes acid. Manna from heaven, food, right? It comes down, and this is what bacteria do. They break down food. This is their thing. Okay, so they break down the food, and they don't know where that food comes from. They have no idea. That's mystical. The source of that food is mystical. Now, let's say this bacterium has an IQ of 200. He's a brilliant bacteria. What can he know about the GI tract, okay, gastrointestinal tract? Well, some, maybe, if he travels, gets around a little bit, they pass the word among themselves, what's going on down in the colon and, what's happening up, in the stomach and that kind of thing. They may pass a few words around. So he might get out into here, maybe. They're really smart bacteria. But what could they know about, grocery stores, refrigerators, nuclear fusion in the sun, sunshine, rain, tractors, trucks, trains, things that make that food get to the grocery store? What could they know about any of that? What can a bacterium know? See, now we're out into this beyond system. Well, they can't. No matter how clever those bacteria are, no matter how good their science is, they just don't know about sunshine and rain and horses and cows and pigs and farms and fences and grass and all of that sort of thing. Cannot be in their reality. And it's not a matter of them not being smart enough. It's a matter of it, they can't get out there. That's not a realm in which they can perceive. If you cannot perceive in that realm, it's beyond your knowing. So that's the first step, and I've told that to a couple of scientists, and man, they get real depressed. You mean I can't know everything? I mean, that's the goal, is to know everything. No, you can't. You have to have limits to your knowing. Okay, so that's kind of the same shape that we're in. So the failure to be able to answer that question, well, what happened before that? Well, this is the reason. You just can't go there, What happened before that is not a reasonable question for us to be able to answer. All right, so those are the two assumptions I talked about. All I want to say here is that you have to understand the difference between a set and a subset. We are in a subset. Consciousness is the superset. The subset cannot describe the superset. The subset doesn't contain everything that's in the set, the superset. So we're in a subset. We're limited to what we can know about the subset. We cannot define it from what's within ourselves. So what I'm saying is, you're not going to define the larger reality of consciousness from the physical tools that you have in the subset. That's impossible. It's logically impossible. Subset can't define the superset. The superset defines the subset. So you have to have these, we have two assumptions. The first one is that consciousness exists. Again, we said that the primordial cell is just a potential energy medium that can differentiate between two states. Well, that's just an assumption, and that's kind of the grab in the air kind of assumption, right? But that's not a weakness. If somebody that believes that the physical is all there is, they say, well, that's a weak assumption. That's not good, but that's not true. If you're going to have a theory of how the superset works, you have to have at least one assumption from the superset. You have to be able to have an assumption that reaches to that superset. You can't define the superset just from data that's inside the subset. So it's required. You'll never get out of that subset if you only use data and information that's inside the subset. It's impossible. It's illogical. So this is our one mystical assumption, if you will, and that's that consciousness exists. Not a big stretch. We know consciousness exists. The rest is just conjecture that it existed and grew and evolved. That's just because that seems natural. And this other one, that evolution exists, that there is this fundamental imperative that things that can change will change to better themselves. It seems like a no-brainer, right? And we know that exists here from the physical viewpoint. So those are the only two assumptions. All right, well, let's do a little summary of what we got so far before we we get into things that are a little less physics and a little more metaphysics. Okay, consciousness is best modeled as a superset, a self-modifying digital information system capable of computing virtual realities. Okay, so there's Fredkin's virtual reality, there's Brian Whitworth's virtual reality that does better physics than objective realities. The larger consciousness system evolves by lowering the entropy of the system. It lowers the entropy of the system by organizing the bits at its disposal in a more profitable, at a lower entropy configuration. Content creation and reorganization opportunities are generated by using consciousness intent to apply free will choice to incoming experience data. Okay, now I use some new concepts there. If you have an information system and it's evolving and it's lowering its entropy, how can it do that? It has to make choices, right? That's part of that feedback. Well, it can make good choices or bad choices. It has the free will to make choices. You cannot have an evolving system without choice, without free will. If there's no free will, then there is no choice and there is no evolution. There's no evolution, there's no growth, and you're kind of stuck. You know, there's no motion. So free will is required. Then you get feedback allows us to modify. So that's kind of where we've come to here, all right?